Our first speaker for this session is Andreas Reiserer from MPQ, and the title of his talk is Quantum Networks with Rare Earth Dopants. Andreas, the floor is all yours.
So thanks. So the idea of this talk is to give a general introduction into the hardware side. So now we've heard a lot about applications already or software in the last talks. And now I'm bringing the audience back to hardware and to the question, what does it actually take to realize entanglement assistant communication networks? So let me briefly start with an overview of quantum networks over some specialty. So we've already seen that there's quite many applications of such quantum networks, and that's very much in contrast to other physical platforms, which are maybe good at one of these tasks. For example, superconducting qubits might be very good at quantum computation, but they are maybe not so well suited as sensors. Or the other way around, NV centers may be good sensors, but maybe they're not very good at simulating quantum systems or so. For quantum networks, the story is different. So these will find really applications in all fields of quantum technology. And the reason is that they have an advantage, an intrinsic advantage, and this advantage is that they are hybrid systems. So in a hybrid system, you combine two physical entities in such a way that the disadvantage of one of them is compensated by the advantages of the other. Now in quantum networks, you take optical photons, ideally in the near infrared. Those have a unique property. They allow you to distribute quantum states at the fastest possible speed, which is of course the speed of light. At the same time, these photons can be coupled to a glass fiber and transmitted over many kilometers before they get absorbed. So that's really unique for communicating quantum states, but it's a disadvantage for applications in which you want to keep quantum states and manipulate them, just because these photons tend to leave your range of influence at the fastest possible speed. Therefore, for applications such as sensing and computation, quite often other physical systems are employed. And a candidate that has maybe emerged in the last decades is spins in a solid. These spins have a unique property. They are very stationary quantum bits. So an impurity atom in a solid that's stuck there, it won't go away. It's basically trapped forever, and it can keep its spin for a very long time, up to 6 hours. Well, this is an advantage if you want to keep and manipulate quantum states. It's kind of a disadvantage if you want to connect them over distance, just because these spins are really stationary quantum systems, meaning that they are well isolated, not only from the environment, but also from interactions with one another. Now, the idea of a quantum network is really to combine the physical advantages of both of these systems in order to have stationary quantum bits that are connected in a fast way by light. It's one of the unique situations in life which allow you to eat the cake and still have it, right? Now, the only thing that's really required to implement such a network is a system which provides you with the stationary quantum bits, but that also have an efficient and coherent optical interface, right? And this talk is focused on the rare earth doped approach to this challenge, because the rare earths, are also called Lanthanides, are very promising in that respect. So let's take a step back and look at the physical spin qubit, the system. So ideally, what you want is a system that's isolated from another way. If a single qubit which does not interact with anything else but the radiation you provide to it. Unfortunately, in a solid, that's not really the situation that you encounter, but you will have decoherence of this spin qubit, which is provided by the coupling to electric and magnetic fields. And in any crystal, you will have a lot of sources of electric and magnetic fields. For example, you will have isotopes which have a nuclear spin, and in this way have a small magnetic moment that couples to the magnetic moment of the spin qubit. Also, no crystal is perfect. There will always be some impurities, stacking faults, other trapped atoms, which are often paramagnetic and then also coupled to the spin. But those can also be charged and then coupled by electric fields to the qubits if they change their charge state. And also any solid will be finite, so you will have states at the surface which also have charge and spin properties that can couple to the qubit and lead to decoherence. And finally, also the lattice can vibrate. So you have phonons and this lattice vibrations. So they will also create fluctuating electric fields by moving the charges of the nuclei, the surrounding nuclei. And those could also couple to the qubit and lead to decoherence. Now, the challenge is to find a system which is not sensitive to all of these sources of decoherence. And in that sense, rare earths or lanthanides are really very promising. So let's have a look at these lanthanides. So if you try to find them in the periodic table, they are in the section which is quite often in the lecture halls is hidden, because it's to chemists it's not a very interesting region. So let me quote a textbook where they say that lanthanum has only one oxidation state, the 3+ state, and with a few exceptions, this tells the whole boring story about the other 14 lanthanides. Right? So for chemists, they are all very similar, have very similar properties, and then that's also why they are difficult to separate chemically. But that's a story for chemics. Now let's go back and look at them from a physical point of view. The reason why they are very similar from the chemical side is the order in which their orbitals are filled and their spatial extent. So here, for example, you can see the wave functions calculated for gadolinium ion, I think. And you can see that with larger main quantum number, the size of these orbitals is increased. So the 6s shell is much larger than the 4f shell, for example. But at the same time, there's a peculiarity in the energy levels of this, in the sense that these outer lying shells have lower energy, lower eigenenergy than this 4f shell. So that's, if you remember Hund's rules and you fill these orbitals with electrons, it's energetically favorable to first fill the 5s, 5p, and 6s shells before you start adding electrons to this 4f shell. Now I tried to find an artist's view of this situation, and I found it in a museum in Munich, which is called the Lehmbach House. So about 100 years ago, Kandinsky has drawn a rare earth crystal, and here you can see a zoom in. Basically, what you can see is that you have the nucleus and the filled inner shells, which are not so relevant for our application. But what you can also see is these outer filled 5s and 5p shells in the 3+ oxidation state, right? They do the binding to the crystal. They do all the chemistry, right? They are responsible for the fact that these rare earths all look the same chemically. But they really surround these inner 4f shells like a Faraday cage, which means they shield the electric fields of the crystal, of the surrounding ions. And in this way, electrons and nucleus, basically, in these electrons in these shells can have very extraordinary coherence properties. Now, if you look at these energy levels in a bit more detail, it turns out that typically you name them by the spin quantum number, the magnetic, the orbital quantum number, and then the combined magnetic quantum number of spin-orbit coupling, right? And it turns out that, of course, you also then have the MJ quantum number, and in free space, these MJ quantum numbers. So all orbitals with the same main quantum number J, but different MJ, will be degenerate in eigenenergy. Still, these orbitals look quite different. So some of them are maybe more prolate, some go to other directions. And this means if you start to place these elements in a crystal, they will have a slightly different overlap with the surrounding nuclei, the surrounding elements. And in this way, they will have a slightly different energy. And that's what we call the crystal field splitting. Now, what's very remarkable about these rare earth ions is that this crystal field is only a perturbation to the spin-orbit states. So if you calculate the energy levels, for example, of dysprosium, you first have to consider the electron repulse and the spin-orbit coupling, which sets the energy levels that you expect to observe in spectroscopy. And then the crystal field is only a small perturbation to these spin-orbit coupled states. And this means, and it doesn't matter in which crystal you look at the energy levels of rare earths, they are always at very similar frequencies, independent of the host material. Still, these crystal fields, they provide a large number of orbitals, right, or a large number of levels. And now challenge experimentally is how to encode a qubit in those. right? Because qubit is often just modeled as a two-level system, and the solution is actually to just go to low temperature. Because these crystal fields, a typical splitting is on the order of a terahertz, right? So at cryogenic temperatures, say liquid helium temperatures, the lowest of this crystal field will be populated with 100% probability. Also, at these low temperatures, you have the additional advantage that all phonons, basically the density of phonons is very low, which means that out of this state, you don't go to excited states, you don't couple to them, you don't have decoherence via phonons. Still, if, for example, by emission of an optical photon from a higher lying state, if you decay to one of these crystal field levels, there's a large phonon density of states, which means that you're decaying very quickly down to the ground state. So there's a large density of states, but there's small population at cryogenic temperature. So in other words, if you want to operate such rare earth crystals, you need to go to liquid helium temperatures. At room temperature, these systems cannot work, but at liquid helium, they work very well, as we'll see in a few minutes. Now the question is still, which of the rare earth elements do you want to take for your quantum applications, quantum networks? And it turns out that there's a fundamental difference between the two, and those is how much electrons are in this 4F shell, because that can either be an even or an uneven number. Whenever you have an uneven number, basically you have one unpaired electron, and this means you will have a strong magnetic moment, and the levels will be two-fold degenerate and only split in a magnetic field, right? And these ions, so all with uneven electron numbers, are called then the Kramers ions, because Kramers theorem dictates this two-fold degeneracy. Okay, so there's two fundamentally different types of ions. There's the Kramers and the non-Kramers ions. Let's first look at the Kramers ions. So if you apply a small magnetic field, then the degeneracy of the ground state will be lifted, and you end up with a level scheme that is actually very simple. So you have an effective two-level system in the ground state and an effective two-level system in an optically excited state. And this means for experimentalists, that's very attractive, because if you, for example, measure if the qubit is in that ground state level and you get a negative result, you automatically know really the state of the system, because then you know it's in the other ground state. And that's a large advantage compared to systems that have more levels. Still, these two-level systems are, so these qubit systems are sufficient to encode quantum information and do everything that you want. Another peculiarity of the Kramers ions is that they have a very large effective G factor, and this stems from the large orbital angular momentum. So as an example, for example, erbium dopants, they have effective G factors up to 16. And this means they have a very large sensitivity to magnetic fields, which is good if you want to use them as a sensor. So they can have 8-fold higher sensitivity as compared to example in V-center. It also means that you can have very good coupling to microwave fields, which is interesting if you want to transduce microwave photons to the optical domain. But at the same time, of course, this is a disadvantage if you want to isolate the spins from interactions, right? Both with external fields, but also with one another. So if you have a high concentration of these Kramers ions in a given material, they will interact quite heavily, and that will destroy the coherence. So with these Kramers ions, you have to really go for low dopant concentration of only a few parts per million. And that can be a drawback if you want to implement memories, but I'll come to that a bit later. So it's difficult to use them as good quantum memories because they're sensitive to magnetic fields and you need low concentration, thus low absorption. So let's turn to the other type of rare earth dopants, the non-Kramers ions. They have a quenched magnetic moment because they have an even number of electrons in this 4F shell. Still, the degeneracy of their ground states is typically lifted by their nuclear spin. Right? So it's not a single level in the ground state, but it's depending on the nuclear spin state. For example, for europium, it's a 5½ nuclear spin. So you will have 6 levels in the ground state, and if you apply magnetic fields, that they will also split. Still, these systems have a very small effective G factor because the nuclear magnetic moment is just 4 orders of magnitude smaller than electronic spin moment. This means they have a weak coupling to microwave fields and then also low sensitivity to magnetic fields. And this actually means that they also don't hardly interact with one another. So you can have really high concentration of dopants in such crystals, a few percent. And this is all good if you want to have long-term quantum memory. So an efficient quantum memory. Efficient is possible because you have many ions that can absorb. And long-term coherence is given by the fact that the interaction with magnetic fields can be very low. Okay, but there's a disadvantage of those also. None of them operates at telecom wavelength, so you would need frequency conversion if you want to use those. So let's now take a even closer look to the source of decoherence. So we've seen by the electronic shell that the qubits can be protected from electric fields, and if you take specific rare earths, you can also be well protected from magnetic fields. But a closer look to the electric field, decoherence tells you that even in spite of this Faraday cage effect, you still have some coupling to electric fields, and this coupling, the strength of it depends on the crystalline symmetry. So there is now two possibilities how you can avoid fast decoherence. One is that you use crystals which have a very low defect concentration or a large band gap. The reason for this is that basically if you have defects in the crystal, they could change their charge state and lead to decoherence. But if the band gap is large, then the energy, in particular at cryogenic temperatures, the energy will not be sufficient to change the charge state, right? So that's the reason why many experiments are done in isolating systems such as YSO or EACN or IVO, which have huge band gaps. We recently also did experiments in silicon, which doesn't have a large band gap, but a very low defect concentration. So it's the purest crystal that you can buy. Another issue about the charges is that you have to worry about surfaces, but because at surfaces you will always have dangling bonds and things can get absorbed, desorbed, which means that you have fluctuating electric fields. So it's difficult to use rare earths in a nanophotonic structure unless you use a crystal which has inversion symmetry. So if you have a crystal with inversion symmetry, then you have no coupling to first order to electric fields, so no linear Stark shift, again because of symmetry considerations. But of course, you may have a second order Stark shift, so quadratic Stark shift. So even in such crystals, you will be sensitive to charges at the interface that lead to spectral diffusion and potential decoherence. Now, taking a closer look at magnetic field decoherence, I already mentioned that you can use nuclear rather than electronic spins, which gives you less sensitivity. And one option is to use the non-Kramers ions, which have no unpaired electrons. And there's a recent alternative, which has been pioneered by Matthew Sellers. And the idea is to use a Kramers ion, which is a very strong magnetic moment, but then you apply a very large magnetic field and low temperature. So several Tesla magnetic field and ultra low, say less than 2 Kelvin temperature. This means that you can also freeze the spin of the system to the ground state, right? And then you can basically proceed in a similar way as in the non-Kramers dopants. You can just encode qubits in the nuclear spin, and again achieve coherence times in the range of seconds in that paper. But that's technically limited, not fundamentally limited. Still, if you want to also the remaining coupling, so even though the coupling to nuclear spins can be weak, that there will be some decoherence arising from that. And if you want to avoid that, you would basically operate in a magnetic vacuum. So you would use a host crystal that consists of elements without or with small nuclear spins, such as silicon, oxygen, and carbon. Those are the main candidates. And you also want to have a very pure crystal with a low dopant and impurity concentration to avoid, as mentioned, spin-spin interactions. In addition, you can use dynamical decoupling, and this has also been shown to work very nicely with rare earth dopants, and this can really give another boost to the coherence times. And finally, there's also another thing that you can do, and this is to apply a specific magnetic field where the coupling to nuclear, the level shift because of magnetic fields is just reduced or close to zero. So in that figure, you can see the levels of europium, in this case, europium and YSO, which are at zero field. Then you have a twofold degeneracy of these hyperfine states. And then at last, if you increase the field, they first start to split linearly because of the Zeeman effect. But then at higher fields, you have crystal field mixing, which leads to avoided crossings. And these avoided crossings mean that you have regions where if you change the magnetic field, the separation between the energy levels won't change. In this way, you can be very insensitive against fields and magnetic fields, and thus keep the coherence of qubits for very long. So in this europium doped YSO material, people have observed 6 hours of coherence by using exactly that trick. While this is already promising for quantum memory, you also have to worry a bit how to get light in and out. So you need a system that has good coherence, as mentioned, and has efficient coupling to light fields if you want to use these systems in quantum networks. Unfortunately, the rare earths are very bad at this because the transitions out of the 4F shell, they can have a high, they can be fast, but unfortunately they don't have this Faraday cage protection. And the transitions within the 4F shell, which have this protection, they are forbidden by dipole selection rules, by symmetry, unfortunately. So electric fields will not couple them. If you take a crystal with very low symmetry, you can improve a little bit. So you have such so-called forced dipole transitions, but still the lifetime of these elements will be very long, on the order of milliseconds. And therefore, you either have to take many dopants and use collective effects to enhance the emission, or you have to use optical resonators and by the Purcell effect, bring these lifetimes down to still enable high rates. The good thing is the lifetime is long in these elements, but also the coherence time is long. And as an example, the narrowest feature, or the longest optical coherence times ever measured in any solid has been achieved with erbium doped YSO, where really you have a sub 100 Hertz line width of the optical transition. And this means even with a moderate Purcell enhancement of 60-fold, you can really have lifetime limited emission of these emitters, which is important, of course, for all quantum applications. So with this cavity-based approach, you can, of course, realize a quantum memory. So you can take individual dopants, and by enhancing their emission with a cavity, you can have still moderate, but maybe high enough rates. But the bandwidth of this memory is of course low, just by the small coupling still to the field. At the other hand, this memory has a very high multiplexing capacity because each of these dopants will emit at a slightly different frequency because of a slight different strain experienced by the crystal. And this means that if you have, for example, a gigahertz homogeneous broadened line, because of these strain variations, you can maybe resolve 100 or even 1,000 ions in spectral domain. So instead of time domain multiplexing, you would, in that approach, rely on spectral domain multiplexing, or if you want to call it an extreme dense wavelength division multiplexing. There's also an alternative. You can also just use many of these dopants and use collective effects to enhance the emission. And this then gives you very high bandwidths. But unfortunately, this comes at the price that you don't have a non-linearity in these systems for processing or for single photon generation. It's then more difficult. But still, the setups, as you can see here, they can be less complex than embedding dopants in the resonator. Finally, with these ensemble memories, of course, you can use different protocols. And in view of time, I try to be very quick. So there's 3 different protocols that have been used. It's electromagnetically induced transparency, which is not so well suited for these rare earths. There's 2 that seem better suited. It's the AFC atomic frequency comp and the gradient echo memory. And they all are based on first spectral tailoring the absorption features, and then periodic or controlled rephasing to read the stored fields out. So to summarize, I hope that I could convince you that rare earth dopants can be a very promising system for distributed quantum information processing or quantum networks. They have really very long, exceptionally long ground state coherence times, so seconds for Kramers ions and then hours for non-Kramers ions. Their excited state can have lifetime limited coherence, which is also important for optical interfaces. They have a very high multiplexing capacity, and some of them, or one of them, erbium, also emits really at the C-band of optical communication, which is advantageous for long distance. There's still ongoing research in the systems. The main challenge is if we can really generate large scale and many node entanglement at significant rates. And I think the community has made great progress in the last years, and I'm sure that in the next years this should become feasible. And still there's also a lot of materials research in the question, what is the best host? So I basically gave a quick introduction. So probably you will need one site with inversion symmetry that you have no linear Stark shift. You want to have material without nuclear spins to have better coherence. And finally, you want a material which allows you to fabricate nanophotonic structures based on established processes. And I think there's now some ideas are followed by the community, and I think some of them are very promising. So with this, I'm at the end of this introduction. I took a little more time because I already answered the standard questions. So I don't have to answer them again, but just can directly ask for your questions.